cosa in spagnol y en italiano, Claudia.
Ah, ok.
Sí, sí, sí. La misma.
También en español y en...
Yo no hablo español. Yo hablo inglés, francés, no español. Lo siento mucho, señor. Lo siento mucho.
But English is okay.
Oh, English is perfect, because today we have to speak English all the time, as you know.
Okay, in this moment, you have your lecture is an streaming for the YouTube Institute.
Yes, thank you very much. Okay.
And I hope see many people.
Okay, so do I.
People, yes.
Okay, good.
Maritza
Now,
said,
let me ask you just a little courtesy. I know that I have... Oh, thank you. Thank you very much, Maritza. I know that I have 1 hour of time. But since the presentation is rather long, I would appreciate if you could let me know, or you, Maritza, say 10 minutes before, so I can regulate myself.
¿Está prendido? Is it on? So,
pues regúlale el volumen, chécale que esté.
No, es que a lo mejor
I'm going to ring the bell just a moment.
Sorry.
No, it's okay, it's okay. Do.
No, sí se escucha.
Perfect, perfect, thank you.
No, sí. Ya más hay que regularle allá arriba.
No, es que estaba abajo en el otro botón.
Ah, ok.
Ya.
So let me just try.
No, todavía no. Ahorita.
Perfect, yeah. Very good. Is that the laser pointer?
The pointer is this? No.
This one?
This one.
Okay. So what are these two commands about?
Don't use.
Don't use. Only beep.
Forward and back.
Okay.
And pointer.
Okay, very good. Thank you very much. Perfect. So what are you? Are you working in astronomy or something?
Yeah, I'm working.
Yeah. What is your field?
Technical computing.
Yes. Very important.
So very important.
Yes, numerically, right?
Computers don't work. The computer.
I know.
And in this age, the computer is old.
Of course.
So if not have working, it's not have working computer.
Yes. The world has changed, I know. No longer as it used to be a long time ago.
Yes.
Everything is done, but even the calculations. Let me sit down just a moment. Yes. Even the calculations are done by computers, you know. I mean, I have...
Ya no lo escucho, Francisco. Maritza, ya empiezo.
Ya la grabamos.
Ah, ok.
Lo grabamos.
Ah, ok.
Por eso te iba a preguntar. ¿Ves que es como...
Okay.
Ya lo tengo, pero se me olvidó mandar el correo. Ya no me han insistido, pero de repente me dijo. Porque nadie más lo pide, ¿no?
Sí.
Y en este caso, pues va a quedar grabado.
Sí, ok. Sería bueno al final estudiante para que haga su servicio en ese que te ponga.
No, lo que pasa es que un estudiante de
So let me ask you, what is the exact time, please?
well, my time.
Yes, your time.
12.
Okay, good, thank you.
But the time is...
I know, it's relativistic, yes. Okay. No, it's fine, it's fine. Let me put it over here so I can see it.
For example, when you pay the stage, the parking. No, my goodness. No, it's other.
Okay. Okay.
Porque si no consume luz.
Oh, I did. See, I did email to the people from history department, and they told me they have a conference.
Did they tell you what?
They had a conference
Okay,
this week.
doesn't matter.
So,
I'll come next time.
Yeah, some of them will try to come, but yeah,
That's
they
okay.
informed me that.
Thank you. Any reaction from Professor Lascano?
I called laboratory,
Yes.
and his students told me that I emailed them all your information and
Yes.
your talk, and they told me they were going to spread it.
Okay, the news. Okay.
So I don't know if they are coming. I only sent the YouTube link, so
Okay.
they say they will try to come.
Of course. Now, let me ask you, what is the average mathematical background of the people in the room?
Well, most of them come from history, although we have some engineers, and I don't know, actually, we have some like a real mathematician. We don't have a theoretical department in this institute, so they do a lot of
Yeah.
but like, I guess the mathematical background for most of them must be the one of the physics.
Yeah, that's fine. That's fine. Good, good, good.
Here we work a lot.
Because, you know, I have to take that into account according to different conferences that they give. So if they know about mathematics, I can push more. If they don't, but this is not the case here, I can just use basic words, skipping, you know, the equation. Yeah, good, 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 good. And what about the director, Jesus, that I was really glad to meet yesterday? Yes.
A la 1 de la tarde desconecta el celular de aquí y conecta la 28 al auditorio de allá. Ya. Ahora, están avisados los de aquí, me preguntaba mi jefe Javier.
¿Cómo?
Javier, mi jefe, me preguntaba si avisas
Avisa a todos.
Ok, es lo que dije, ya, yo dije, ya.
No, avisa a todos que quieran ir a reunir y puedan a las 2 y que le vamos a contar a la 1. No seguimos entonces con la producción, porque seguramente seguiremos aquí con preguntas.
Sí, yo me voy en chingo.
Yo voy a estar aquí.
Muy rápido. Sí. Vale. Sí. Hasta la 1. Terminando, Claudia.
Sí, no va a terminar a la 1. Yo creo que va a seguir su conferencia.
Yo me sigo por el otro.
Entonces, sí, o sea, cuando ves la 1, aunque no se haya acabado.
Okay.
Vale, adelante. Ya estoy hablando. Vale.
So if I got it right, when it's 1 o'clock, it's over, right?
No. Like what I'm saying is that like the people from Ensenada have another colloquium that starts at 1 p.m.
Oh.
So they wanted me to wait until you finish and they start after you.
Oh,
Like
wow, that's very kind of them.
No, the problem is that I expect you to have a lot of questions. So I don't think we're going to finish at 1 sharp, or even if it's 10 minutes. I don't want to make the speaker wait.
Yes.
So I asked them to, because people from here also want to attend that.
Yes.
So they are going to go to another room here.
Yes.
And they are going to call Ensenada.
Yes.
But so we'll have to cut the transmission from your colloquium to Ensenada.
Yes. Yes.
So people there might just miss your questions.
But what about here? We can go beyond?
Yeah, you can be.
Thank you. That's very kind of you, because I know that there will be questions here.
Yeah, like this is a large audience.
Nice to meet you again. Thank you very much. Nice to meet you.
So this is a more than average audience, I think. Never see it.
More than average? Very good. Very good. Okay, well, it's fine, yes.
Hello, everyone. So we're going to start the colloquium today. So it is my pleasure to introduce you Professor Claudio Macone. So he's visiting us he's the Director for Scientific Space Exploration of the International Academy of Astronautics. He's also the Chair of SETI at the Permanent Committee of the International Academy of Astronautics. So I'm going to, he has, of course, a very large curriculum, so I'm just going to tell you a brief summary. So he did his PhD in the University of London King's College. He also has a Fulbright scholarship at the Polytechnic University of New York in the US. After that, he joined the space group of Air Italia, now it's called Alenia Spazio, in Turin, as technical expert of the design of artificial satellites. He has published several books, and some of them also have won important prizes. And one curious note is that the asteroid 11264 was named after him, as Claudio Maccone, by the IAU. He also was awarded the Giordano Bruno Award by the SETI League for Technical Excellence in the SETI service of SETI. So in 2001, he was named the Technical Director of the International Academy of Astronautics for Scientific Space Exploration. So this is the charge he's currently on. And in 2012, he was elected chair of the IAA SETI Permanent Committee. And so today, Professor Maccone is going to talk about his new theory named Evo-SETI. So he's also very excited of being here because one of the important parts of his theory is a comparison between Aztecs and Spanish. So he's very happy to be here where Aztecs were. So we are all yours. So.
Well, thank you very much, Maritza. Thank you very much. And good morning or good afternoon if you prefer. I'm really glad and honored to be here. Yesterday I had a very nice conversation with the director, Jesus Gonzalez, about a topic which is rather unusual for astronomers, which is SETI, the search for extraterrestrial intelligence. So let me say that I started my career, of course, as an astronomer. So I did my work, PhD, and so on, at the Astronomical Observatory of Turin, Torino, in Italy. And then I prefer to shift to the space missions, because space missions today are very important. And the occasional reason for which I am here in Mexico today and in the following week is that, as you probably know, next week there will be a big conference in Guadalajara. This is called the IAC, standing for International Astronautical Congress. It is held for the first time in Mexico, and it's huge. I would expect 2,000 or 3,000 people in Guadalajara, because this is about all kinds of space missions, you know, from scientific space missions, which are the ones we are interested in, but also to other exploration, also astronautical flights and all that. Now, in this big conference, I am responsible for the SETI part. So SETI is Search for Extraterrestrial Intelligence. And I have to say that the general interest in the world, not only in single countries, in SETI is actually increasing in time. So I have been in this business for about 20 to 30 years. And 20 years ago, the people interested were very small, very few people. But nowadays, I am glad to say that for the Guadalajara conference, I have accepted 27 abstracts for presentation. So it's really a good point. And I have to say that next year, about this time, the similar conference will be held in Australia. Adelaide is the town in Australia where it will be held. And in the following year, 2018, it will be held in Bremen, Germany. So as you see, the conference is being shifted in different places in order to help everybody. Good. So thank you very much, and let's start with this presentation. Now, first of all, I have to apologize if I am publicizing my book, but I think that if anyone in the audience is interested in pursuing more the studies of SETI, the search for extraterrestrial intelligence, this book could be of interest. It's a big book, and I have to say that it is not a popular book. I wrote it intentionally, as the title says, as mathematical SETI, because there are so many beautiful books about the popularization of SETI, what are intelligence, and so on and so forth. But what we need here in the community of astronomers and scientists, more in general, is a textbook with all the equations so that the students come to learn, don't have to read many different papers in different journals. And so I think it's a good textbook for SETI courses. Okay. And now let me summarize very, very briefly what SETI is, what the historical development of SETI was, at least in a few slides. Of course, there would be much more to say, but I don't have the time. So let me start with the beginning of SETI. Now, of course, prior to 1959, the philosophers had already speculated about the existence of possible extraterrestrial civilization. I just would like to mention one from my country, Giordano Bruno, and I'm sure that you all know that unfortunately he was burned at the stake in Rome by the Inquisition. So you didn't have only here in Mexico the Inquisition, we had it also over there. And I'm terribly sorry about that. There is a monument now standing where he was burned. So anyway, apart from the philosophers, the real SETI science started in 1959 with the famous paper now by Giuseppe Cocconi and Philip Morrison. They are the two gentlemen over there. Cocconi was a physicist of the School of Fermi, and Morrison was a physicist at Cornell University in the United States. So they published this paper. Now, the important point about this paper is very easy. They proved mathematically that it was possible, and it is possible, to communicate between nearby stars by using electromagnetic waves. This is the point about the paper. So they open up really the field of SETI, because before them, even scientists had doubts that it was possible to communicate with electromagnetic waves across interstellar distances. Now, of course, electromagnetic waves travel at the speed of light. So this means that if we want to receive a signal from Alpha Centauri, that will take 4.37 years, because this is the light years distance from Alpha Centauri, and even more from other stars further out. But we cannot do anything about that. This is how the universe is shaped. This is how physics is shaped. So this was the first thing. And then the graph on the right is essentially an idea that the atmosphere, which is forbidding radio transmission on many different bands, is, however, allowing this law. You know, here is impossible, but over here, in between 1 and 10 gigahertz, it is possible on the surface of the Earth to receive radio waves from wherever they are emitted. And this is very, very important, because at the end of the Second World War, two famous theoretical physicists, Van de Hulst in the Netherlands and Josi Shklovsky in the Soviet Union, proved that when you have the hydrogen atom, then, let me show it in popular terms, you have a spin transition. So this is the proton and this is the electron. The electron, apparently, turns out, this is not, of course, the formulation in quantum physics, but just to make things easy, this is the case. Now, in the lowest energy configuration, the two spins are anti-parallel, right? But actually, since all the hydrogen atoms are immersed into a huge radiation bath, it happens that spontaneously the electron turns on the other sense of the rotation. So this is called the spin transition. And when that happens, radio waves of the frequency of 1.24 whatever gigahertz is absorbed or emitted the other way around. So the conclusion is very important, that all the hydrogen atoms in the universe undergo this spin transition. And we can pick up the radiation if we have radio telescopes on Earth. Now, more, the width of the bandwidth on which this radiation is picked up is proportional to the number of atoms in that direction of the beam. So the moral of the story is that by 1960, roughly, especially in the Netherlands, the radio astronomers were able to prove forever that the solar system is within a big spiral galaxy about halfway between the bulge, say 25,000 light years away, and the outer edge, similar 25,000 light years away. And they were even able to map the spiral arms of the galaxy by virtue of this radiation. So this is extremely important for radio astronomy in general, but also for SETI. Now, after that, Frank Drake from the United States immediately started using the radio telescopes at Green Bank. Green Bank is in West Virginia, is the National Radio Astronomy Observatory of the United States, to look for signals. He couldn't find signals. Up to now, we did not find any extraterrestrial signal, but nevertheless, the search has started. And now I am going to make a big jump. I jump to the year 2009 when the United States launched the wonderful Kepler space mission. I'm sure that most of you know about that. So this is the Milky Way galaxy with the arms. This is the sun, and the orbit of the spacecraft is around the Earth, of course. But the point is that the depth on which the beam can still pick up the light of stars is about 3,000 light years. And the part of the sky that is explored is extremely narrow, just a very small window around the Eagle constellation and so on and so forth, Lyra and so on. So what we have done in this mission is just to open a very small windows in the sky. But nevertheless, even if the window is so small, we were able to discover over 3,000 planets. So this is a great result because it means that the galaxy is full with planets. We now have the proof, at least for this case, but we are going to send more missions. So this is a wonderful result. Just to give an estimate, we estimate nowadays that in the Milky Way galaxy there may be 300 billions of planets or something like that. Of course, of different sizes, so the Earth is just one small set, but doesn't matter. So this is the situation. Now, please let me tell you about my work on space mission, because this is related to SETI and is now under consideration by NASA, so it will become sometimes in the future a real mission. I am sure that most of you here, you know what a gravitational lens is. So this picture shows, for instance, that at infinity in that sense, there is a source of radio waves, whatever it is, a radio galaxy, a quasar, even an extraterrestrial civilization, whatever emitting radio waves. So the radio waves reach the sun. This disk here is the sun. And the gravitational field of the sun inclines the trajectory of the radio waves so that the radio waves are made to converge on the other side with respect to the source, right? Now, in general relativity, you can do the easiest way is to use the Schwarzschild solution, but you can use more refined solution like the Kerr solution and so on. Anyway, the point is that if you use the Schwarzschild solution, you find that the minimal distance in between the sun and the minimal focal point, that is, the focal point that we have to reach with the spacecraft in order to take advantage of this. Otherwise, we are too close and we do not see anything. So the minimal focal distance is 550 astronomical units, which is 3.17 light days, roughly half a week, light week, okay? So it is distance, but it is not impossible to imagine that in the future, in the next 50 years, 100 years, we will be able to send spacecraft. So I'm really glad about this because I have to say that I published my books about that time ago. The last book was in 2009. The title is Deep Space Flight and Communication. Now these books are used as textbooks. For instance, at Harvard, I was surprised to see that the students use my book about this topic. So NASA is taking care of that, and the young people in the audience will probably find the space mission. Now, this was the introduction, but my talk, as I said, was not exactly about that. This is wonderful astronomy, but we have to try to adapt the talk also to the audience. So as it was said previously by Maritza, I have tried to develop a mathematical model or mathematical theory that I called Evo-SETI. Evo for evolution, SETI for SETI. So it's a mixture of both Darwinian evolution and SETI, in order to find out how life may have developed on other planets, since we know what happened on this planet. In other words, we know from Darwinian evolution, biologists tell us, that life on Earth developed roughly from 3.5 billion years ago. And then it developed slowly until it reached us, okay? Now, this is the only case we know about the development of life. The question is, can we set up all these into mathematical equations, which are, of course, statistical. You cannot predict anything with certainty, so you must resort to statistics, so that we'll be able to make some prediction about the extrasolar planets and whether or not life may have developed or may be developing or will be developing in the future on those planets. So this is the topic of this presentation. Now, just to give you an idea, first of all, I have to say very quickly something about the statistical Drake equation. Then is nearly the same, the statistical big history equation. Then I have to go over to something more mathematical, but since I know that this audience is mathematically trained, I am not afraid to write down some equation. You know, in other conferences, they would not write down the equations because then the people would feel scared somehow. But this is not the place here. So I will have to say something about the log normal distribution, not the normal, the log normal distribution in probability. Then the Darwinian exponential growth, which is the growth of the number of species over the time. Then I have to mention something that is, unknown even to physicists, to many physicists. I'm really sorry about that because I regard myself as a physicist. But it is known to financial mathematicians. So if you talk to the people in Wall Street who handle lots of money, I don't know whether they handle it well or not, but that's another story. They know about geometric Brownian motion. So I had to take books about mathematics or finances to find the equation and then to translate the story into this kind of biological study. So the name is not correct because it is not a Brownian motion. I mean, we physicists believe and understand that Brownian motion is a stochastic process whose probability density is the Gaussian or normal. But this is not the case because geometric Brownian motion has a log normal probability density. So it's a wrong name. And then you ask me, so why did you keep the wrong name? Because I'm not going to correct the name, because if I start correcting the name, then the confusion increases. So I kept the name, but I want to be clear that it is a wrong name, probably given by the financial mathematician. I don't know. Sorry about that. Then, Darwinian evolution as a GBM, geometric Brownian motion. This is very important because this is the tool I have used to set up Darwinian evolution into mathematical terms. And then the big things arrive. We are all physicists. We know what entropy is. But the entropy that is taught in ordinary physics course, I am afraid, is the old entropy, going back to 1850. Clausius was the German physicist to introduce entropy. That is wonderful, but that is about gases, because in 1950 they knew about the theory of gases. Now, what I'm using here is not that. What I'm using here is the Shannon entropy that was invented, discovered, as you prefer, by Claude Shannon, an American engineer and mathematician who developed the information theory. So entropy in this presentation is about information. That is how much information you can convey across a certain transmission way. And finally, I arrive at the Aztecs and Spaniards. Now, let me tell you that, first of all, I am honored to make a presentation like this here. I have been longing for a long time for a possibility to give this talk here, because this is where the clash occurred in between two civilizations that were very different in the evolution of technology. Now, how much different? Well, I will show you, if I had the time, that in my opinion, this will be something like 50 centuries, because the Aztecs didn't know about the wheels and so on and so forth. But apart from that, if you translate the same story into entropy, Shannon entropy, then you have the important number. The important number is that, on the average, each Spaniard was 3.85 bits more knowledgeable than an Aztec. And that spells the difference in knowledge. Now, why did I do that? But obviously, because as a chair of the SETI committee, if we discover an extraterrestrial civilization, my concern, before any other concern, is to understand how much those extraterrestrials are possibly more advanced than I. You see the point? So this is why I developed the full theory, because there are huge differences in the life of stars, as you know, as you teach me. So we have to figure out what is the difference, whether it's a small one, whether it's a large one, just not to end up like the Aztecs when they met the Spaniards. Okay, and then there are other points, but possibly I'll skip all that. So let me tell you very, very briefly about the statistical Drake equation. Now, this gentleman is Frank Drake. He is the person that more than anyone else influenced my thought and also my career, because he was the greatest SETI scientist. He admitted me into the SETI committee, so I really owe him a lot. Frank Drake, in 1961, wrote this equation. Now, on the left, capital N, is the number of communicating civilizations in the galaxy right now. We don't know it, of course. But then you figure out that this number can be written as the multiplication, all these dots are products, of 7 factors. Now, the first factor is, of course, the number of stars in the galaxy. And we know about that more or less, about 350 billion stars. But then there are other things. The fraction of that number, F stands for fraction. Fraction of that number that have planets, of course. The number of Earths for each stellar system. The fraction of all that where life develops. Now, here we have to be careful. Life in this understanding is life in the sense of animals. So it starts with cells and grows and fishes, whatever, but reaches animals, not intelligent creature, right? And the difference, basically difference is that animals live on instincts for fighting, for reproduction, for food, for whatever. We do not only have instincts, we have something better, hopefully. So the next factor is the fraction of all that developed intelligence. Now, intelligence is what we have and what has allowed us to evolve from animals, from monkeys, up to now, and oh my, up to the communications level. Now, the communication level for physicists or astronomers as we are means the Maxwell equations. It's a wonderful point because before 1864, when Maxwell discovered the Maxwell equation, nobody knew about electromagnetic waves. Electromagnetic waves were first discovered theoretically on the paper as a sinusoidal solution of the differential equation of Maxwell by Maxwell himself. Then other scientists arrived like Hertz, Marconi, and so on, and they proved that this was indeed the case. But before, nobody could even imagine the existence of radio waves because we do not see them, obviously. It's not like mechanics. So this starts from 1864 up to now. And this is the most difficult question. How long may a technological civilization survive? We don't know. We don't know because we have only ourselves as example. So this is the Drake equation. And in the web you can find a number of code that you give numbers for the 7 factor and you find. But let me say that this, is rather childish. I mean, my PhD was in mathematics. So when I found the Drake equation, with all due respect to Frank Drake, no, look, this is an offense to Frank Drake. Let me try to do some better mathematics. And the better mathematics is clearly to replace each factor by a probability distribution. This is much more sensitive because you give a mean value, but you also give a standard deviation on each side. So it's much more scientific. But then it becomes also much more complicated mathematically because you have the product of 7 probability distributions that you do not know, So the next question is, what probability distribution? A Gaussian, a log normal, what? I don't know, an exponential, what gamma, whatever, I don't know. So this is what I did, and I have to be frank. First of all, I had to release the hypothesis that the number of factors is 7, because this is ridiculous. So suppose any number of factors. And when you do that, you are making one step ahead, because, look, we are all mathematicians, or physicists anyway, but the point is that you are tempted to let the number of factors approach infinity. If you do it, then the solution comes out in a moment. So the calculus is a great thing, really. I mean, we enjoy that. So if you have any number tending to infinity, then first of all you take the log. So on the left you have the log of n, and on the right the multiplication becomes a sum, of course, right? But then at this point you can apply the so-called central limit theorem of statistics, which is the nicest theorem of all statistical courses for beginners in some sense, and says that in poor terms, not in rigorous mathematical terms, if you have an infinite sum of random variables, whatever the distribution of each random variable is, so I don't care about that, whatever the distribution is, since the number of terms approaches infinity, then on the other side, the result approaches the normal or Gaussian distribution. This is wonderful. This is the greatest discovery in statistics, made in the 1800s by all the statisticians. Each one reached the same result by different ways, but this is the moral of the story. So this means that log n approaches a Gaussian distribution, okay? And then you only have to do one more step. That is, if log n is Gaussian, what is n? And the answer is, n is another distribution which is called log normal. And this is the log normal. So, this is the first result. This is the equation of the log normal. It's called log normal because it looks like a normal, but here you do not have x. Here you have the log of n, right? This is why it's called log normal. And the profile starts from 0, 0, please, not minus infinity as the normal. Goes up to a maximum and then decreases to 0 at infinity, period. So this is the probability distribution for the number of stars in the galaxy that are communicating according to the Drake equation. And they published this in 2010. And you know, honestly, please forgive me, I was surprised that no one else had discovered this before me, really. Before going to publish this, I met with the big scientists of SETI, Frank Drake and Jill Tarter and so on. And I presented this result confidentially to them to avoid being the stupid guys who goes and publish that and spoils his reputation because someone else already had discovered that. But that was not the case. So this is probably out of my papers, the most read paper, and this is chapter 1 of my big book. Okay, now, these are the papers, the statistical Drake equation, Astronautica 2010, and so on. Now, the big history equation. What is big history? Very easy. Big history is the history of the universe from the Big Bang up to now. So 13 point whatever billion years. But described in scientific terms. So the big historians are basically the writers, the teachers that teach in universities, that describe the history of the unity in popular terms, but scientific, not fantastic. Now, from the mathematical point of view, so this is the Big Bang, minus 13, whatever. From the mathematical point of view, I have published a paper saying, no, look, this is the same thing as the Drake equation, with just one term added in the front. That is, a term telling you, this term here, telling you the unknown number of galaxies to suppose supposed to exist in the entire universe. So mathematically speaking, the transition between SETI, the Drake equation, and big history is just to multiply an initial term that we don't know about. But it is as easy as that, nothing more profound, mathematically speaking. I'm not going to waste too much time, but okay, this is, we don't know, and of course, right. Now, again, we don't know, but supposedly, the time in billion years, 0 is now, in my books, minus times are times in the past, right? And positive times are times in the future with respect to us. So in conclusion, we may imagine, for instance, that the number of civilizations in the whole universe, not in the galaxy, as the Drake equations, in the whole universe, is very, very slowly increasing until suddenly something like, who knows? I mean, this is the time when the Milky Way was born, minus 4.5 billion years ago, roughly speaking, right? So roughly, if things over there are going as they were apparently going here in the Milky Way, then we have any huge increase exponentially and all that. But this is supposition. I don't know. It's just an example. Good. Now, we change completely topic. Oh my, I have to be careful about this because, let me ask a question. Are there biologists in the audience? I want to be cautious, you know, not to be thrown out. Okay, well, good. There are no biologists, so I am fine. But I have to say here that in this university, I have a very good friend. And please, when you meet him, tell him that I was here bothering you with this mathematics and all that. He is Professor Antonio Lascano. Antonio and I are excellent friends. We met all the time. Incidentally, he speaks excellent Italian, so when we speak, I don't speak Spanish, and I apologize, so we speak Italian. So anyway, Antonio, of course, is working in astrobiology, but more precisely in the origin of life. So he is talking basically chemistry, whereas I am talking basically mathematics, if you like. Nevertheless, for my Evo-SETI theory, I had to give an expression in terms of mathematics of the life of any creature that has been in existence, from microbes to us to extraterrestrials. So here is my answer. Life has a finite B-log normal. Now, I have to confess, as you probably understood, that I love the log normal distribution. Log normal distribution is wonderful. Has never been studied as it deserves, in my opinion. Anyway, the point is that if you have your log normal starting rather than at 0, which is stupid. I wasn't born at time 0. Jesus Christ was born at time 0. Not me. So if you start, incidentally, I was born in 1948, so I'm an old guy, but that doesn't really matter. So if you start at B stands for birth, then you have an increasing part that goes up to adolescence, or puberty in reality. Then keeps going to the peak. In Greek, the philosophers call that the acme of a person. Then starts declining into something else, which is senility. But then I cannot use the log normal anymore, because if I was going to use the log normal, the curve would go up to infinity this way. And nobody of us is going to live for an infinite amount of time. So we have to change. Here, at the descending inflection point, we just replace a straight line. So this goes down in a straight line until it meets the time axis, and this is the death. Period. This is my definition of lifetime. Whether you like it or not, but I had to use it. Otherwise, we stumble into philosophy, biology, whatever. I am a mathematician, so I want a simple equation. Otherwise, we do not make progress. So this is it. This is the equation again. But please notice that rather than t, here we have t minus b, because the log normal starts at b, birth. Right? So you have to shift the probability density. I'll cut short over here. I just would like to inform you about this history formula. The name is mine. Why? dark ages in
Welcome
the
to
real
the
sense.
conference.
Thank you. Very kind people, I have to say that. So anyway, then we go over to the Italian Renaissance, which is this one. And then we have Portugal, Spain, the orange one, France, Britain, and finally the United States. Good. Now, when you have plotted all this, what is the next temptation, mathematically speaking? The temptation is to draw the envelope of all that. That is a curve that is really enveloping all of that. Let me speak as a mathematician just for 1 minute. Now, if you go over to the traditional equation of the envelope that they teach in the calculus courses, my God, you are stuck. Awful equation. But if you replace those equations with another thing, which is the locus, geometric locus of the peaks, then an exponential is very good. And this is what I did. Yes? Thank you. Thank you. Now, everybody asked me this question. Now, I am answering. All these curves are Bilog normals, that they are probability distributions. So, on the vertical axis is just the numerical value of the probability distribution, nothing more. So, it's a number higher than 0, but much, much lower than 1. Pardon me? Oh, yes, sure. Now, the important point is that all these areas, the area under Greece, the area under Rome, Italy, and so on, are equal 1. Because this is the normalization condition of each probability distribution. This is fundamental, otherwise you lose the comparison, okay? Okay. So I was telling you about the envelope. These are the equation of the envelope, or more correctly, the geometric locus of the peak. I call it envelope in popular term, but it's not the exact mathematical envelope. Okay, and this is my first discovery. After doing that, I discovered a theorem that I call the peak locus theorem. The peak locus theorem tells you this. Now, forget about that. Well, this is about Darwinian evolution. When you go over to Darwinian evolution, on the vertical axis, you don't have any more numbers, as I was just mentioning a moment. You have the number of species, living species on Earth. You remember that Darwin's book was entitled The Origin of Species, right? So on the vertical axis, you have the number of species. Now, of course, there were many dead species along 3.5 billion years. So the curve cannot be an exponential as easy as that. It must be something much more subtle, mathematically speaking. This something is a stochastic process. That is, a random function going above and below the mean value, such that the mean value is the exponential. And this is precisely what in Wall Street the financial mathematicians call geometric Brownian motion. Okay, so here is the next step, mathematically speaking, in the story. Just a moment, please. Okay, now, the red curve here, I don't want to waste too much time, but let me just tell you this. When we do physics, we find constants of nature. For instance, capital G, the gravitational Newtonian constant. For instance, C, the speed of light. For instance, H, the Planck constant. We do not know why the value is that, but we know that this is an important value that we use in all physics. Now, let me say frankly that I discovered something similar, and this is this thing here. If you represent the evolution of life on Earth as an exponential, capital A times E, the number E, raised to B, capital B times T, and if you suppose that E, that is the number of living species today, is 50 million species, which is what the biologists tell me. If you talk with Antonio Lascano, I guess that he agrees about that, more or less, of course. Then B turns out to be this number. Now, in my opinion, this number is extremely important to understand the evolution of life on Earth, because this number, capital B, gives the pace of evolution of life on Earth, which may be very different from the pace of evolution of life on another planet. So this number is good for Earth, like the solar radiation coming from Earth, fine. But if you change the planet, the number will change. And of course, my goal as a scientist will be to find out the similar values for other planets, at least in the future. Okay. And here is the peak locus theorem. The peak locus theorem is a mathematical theorem, so it is proof. If you have an exponential going like this, and if you set a family of Bilog normals, as long as you move in higher and higher times, the area must always be 1 under the Bilog normal, because that is the normalization condition. But the peak is on the exponential. That thing I call a running Bilog normal, because it runs from left to right. And the equations, this is the Bilog normal. The equation of the running Bilog normals are given by these things. So the peak of the Bilog normal abscissa, the abscissa of the peak is given by this equation, small p. And the ordinate is given by this equation. But the ordinate is the same as the exponential, as we just said. So if you want to go ahead, you equal this expression here with the exponential. In other words, you have to equate these two things. Oh my, this is an extremely easy system of two equations to be solved. When I discovered that, I was so happy, I have to admit, you know. Because clearly, A is given 1 over 2 square root of 2 pi sigma. So A is given by this. And the exponential is given by BP equals sigma square over 2 minus mu. So you discover these two equations that are the key equations for the running Bilog norm. Just that? No, there is much more. You can solve this equation exactly. And this is the solution. Sigma is given by that, but mu is given by this thing. So this is the key result for every further progress in my Evo-SETI mathematical theory of evolution of life on Earth and on other planets. This is the geometric Brownian motion. I'm not going to say much more. This is just a representation. Just to give you an idea, this is taken from Wikipedia. They do the simulation, I just do the picture, and that's it, period. The point is simply that you can imagine the exponential mean value in the center of the curve. Forget about that. I don't have much time, and forget about that too. Darwinian exponential growth as a GB name in the number of living species. It's just what they said. I'll cut short. These are the papers where I proved all that, because you have to be bold and go in front of the world and say, I am claiming so and so and so. I did it. They didn't fire me so far, so that's fine. Oh my, and this is the final good point. Now, so far so good. You have understood everything. I see that you are very well listening to my expression. But now the real point arrives. Entropy. Entropy, I told you, for physics is what about gases, the states, the Maxwell, I don't care about that. What I use is the Shannon entropy. That is the measure of information for any probability distribution. This is a great discovery that was done in 1948 by Claude Shannon. So, let me just show you the equation. This is really important. It's simple, but it's important. So, H, reminiscent of Boltzmann H theorem and so on, because of course statistical mechanics developed and Shannon knew about Boltzmann and so on. Anyway, if you have any probability density f sub x, capital X of x, the Shannon entropy is the integral from over the extension of x of the probability density times the logarithm to the base 2 of the probability density. And if you replace the log to the base 2 by the log, by the log of base A, you get this thing. Now, it is extremely lucky that for log normal and B log normal probability distributions, this integral can be computed exactly. No approximation, a wonderful theorem. It is in my book, of course, you can see it. So this is the result. The entropy of any B log normal, apart from the constant, is given by the log of square root of 2 times sigma plus mu, the other parameter of the log normal, plus 1/2 in bits. So we use bits as an information theorem, of course. Okay, now I translate all that into what I proved earlier, the peak locus theorem, and this is the fantastic result. The result is that if the evolution grows exponentially, as I mentioned, then the entropy grows linearly. So it is just a straight line. Wow, what is better than that? What is easier than that? In biological words, and I'm sorry that Antonio Lascano is not here, this is called, by the geneticist, the molecular clock. L'orologio molecolare in Italian. So it means that in evolution, as it occurred on Earth, the substitution in a DNA molecules, substitution of A, C, G, T that you know about, are, in first approximation, proportional to the time. So if you have two different species, it means that you have, for instance, the molecule of the DNA of a man and the molecule of the DNA of a horse. The difference is proportional to the time, millions of years, since the two species diverged. Okay? And the great result is that, roughly speaking, this is linear, so it grows linearly, which is precisely what the geneticists do every day. This is called, last universal common ancestor, if you go back to the origin, or if you just step to recent more times. It's a linear proportion between the time and the number of substitution in first approximation, okay? So I'm most glad that my entropy is just reflecting that. Because once again, here we are making a real step ahead. They say it by words, but I say it by equations. So that paves the words, paves the scenery for more progress. Okay, let me just go ahead because the time is not much. Examples. Okay, and now I'm coming to the difference between Aztecs and Spaniards. So I give you the result, and then if I have time, I prove it to you. So the difference between Aztecs and Spaniards in 1519 turns out to be 3.85 bits on the average per individual. Okay, so in other words, each Spaniards, when they met, was 3.85 bits more knowledgeable than each Aztecs. Later I will explain how I get that, but that gives you the... it's the information. For instance, the Aztecs didn't know about the wheels. That matters. But I will tell you more about that. Let me go ahead. The difference between a Victorian Briton, Maxwell, for instance, and Pericles Greek, the Parthenon, Aristoteles, whatever you want, was 1.76. And then you come to the big result. What is the difference between humans today and the first ever living species in the biological past? Well, the first ever living species, the biologists tell me, is RNA. And the time elapsed is 3.5 billion years. Well, do you want to know how many bits corresponds in entropy terms? 25 points whatever bits, so much more than the other bits. Okay. I come to the end because I know, no, I forget about this. This is too complicated. I just want to tell you how I reached the result about the Aztecs. When the Spanish arrived here, they were admiring the Aztecs because it was a great empire, excellent. The town, Tenochtitlan, was wonderful. But the Spanish were surprised that the Aztecs did not know about wheels. Now, for Europeans, not to know about wheels was a shocking sign of technological backwardness. However, the children of the Aztecs used to play with little toys that had small wheels with the holes inside. So I used this fact to say that the Aztecs were on the verge of discovering wheels. They just needed a bright Einstein of the Aztecs intending to increase the size of the wheel from the toys to big like that, and then they would have discovered the wheels as the Europeans had. So this is the first point. The second point, how long ago did the Europeans discover wheels? Well, the Europeans, including the Sumerians, and so the Middle East also. You go into books, you read the chapters, and the result is 3,500 years before Christ. So if you sum these two numbers, 3,500 before Christ, plus 1,500 after Christ when the Spaniards arrived here, all that makes 50,000. In other words, the difference in evolution of technology between the two civilizations was 50 centuries, and not just a small number of centuries. I quantify that because if I do not quantify that, I cannot do the calculations. So for me, in my paper, the difference is 50 centuries. Then you do the next step. 50 centuries at that time. So you have to introduce two different bill of normals of the Aztec. The true Aztecs that developed over here in Mexico since 13 whatever, and this is the small bill of normal of the true Aztecs. And another false bill of normal that they call the virtual Aztecs, which is the same as this, but translated back into the time when the European discovered the wheel. Otherwise, you cannot make the comparison because the progress has been exponential. It's not linear. The entropy is linear, but the progress is not linear. Okay, now I save you the equation because I don't want to give a mathematical lecture. But the point is that you can do the calculations, and these are the calculations. Not difficult, but you have to solve numerically one equation because it's transcendental. And so you have to use a Taylor series and all that. But anyway, when you do the calculation, the conclusion is pretty easy. The difference in entropy is 3.85 beats per individual. And this is really everything I wanted to tell you about. I am not going to, oh God, this is the future. So the story of the Aztecs and so on is the past. Would you please let me speak for 2 or 3 more minutes to tell you about the future, because the goal of all this is to foresee the future, not to look only at the Aztecs, the Incas, or the Spanish. Now, in the future, and incidentally, let me confess that I am one of those people studying interstellar flight. Future interstellar flight, of course. We do not have interstellar flight now, but we are working on it. As I mentioned already when I spoke about the sun as a gravitational lens. So I love to imagine the physics of the future and to imagine future interstellar flight. Now, we know that we are in a galaxy. So if you do the calculation, you can imagine, for instance, of course we do not know the numbers, but I just give you the numbers as an example. You can imagine that a civilization like us, in order to expand and conquer the whole galaxy, may take, in my calculation, 22 million years, jumping from one star to the other one. Okay? Read my book and you'll find the calculation. Of course, I may be wrong, but it's just an exercise. So the question is, okay, the time is 22 million years. What does that mean in terms of entropy? That is, if we human want to conquer the galaxy in 22 million years, how much do we have to improve ourselves in terms of information theory, that is in terms of knowledge, that is in terms of bit? And here is my answer, and that is the end of my conference. So my answer is that I just mentioned that from RNA to humans, the difference in entropy is 25 point whatever bits. So it's pretty big. We have to improve that number 400 times if we want to conquer the whole galaxy in 22 million years. And after this, I thank you very much.
Thank you very much. Very interesting. Questions?
I have two questions. As far as I understand, there has been a discovery of a new planet near Alpha Centauri that might be waterborne. So I guess that the possibility of trying to send signals there is enormous. Do you know of any projects of trying to reach a possible civilization there? And the other question is, now with Gaia and all these new planets that will be discovered, I guess the probability of discovering new worlds is much higher than whatever Kepler found.
Well, thank you. They are both very interesting questions, so thank you very much for this. Yes, as you've said, a planet was discovered even to the nearest stars, Proxima, not just Alpha Centauri A or B, Proxima, which is the closest to us, 4 point something light years away. Yes, there is a group of physicists, crazy as you want, that are already planning to prepare a mission to that point. Okay, I make a confession as far as I can say it, because this is not secret, but you know, when you talk about these things, there is money involved, because if you set up a team of scientists to design a space probe reaching Proxima Centauri, these scientists must be bright people, or people who know about space flight and all that. So you have to pay them, and so you need money, and so it's a matter of funding. Unfortunately, this is the reality. Anyway, I just anticipate to you that yes, there is a group under formation that is considering designing a spacecraft reaching Proxima Centauri. You tell me how many years? I don't know. It depends on the propulsion system.
I'm sorry, I meant radio signal.
Radio signal is a different story. Radio signal is 4 point whatever years, period. But here is a problem. The problem is that despite all the progress that we have made in space flight, we do not know well how to keep the radio link between the Earth and the probe at the distance of Alpha Centauri. Because you realize that the probe has a small antenna, an antenna big like that or higher, but it is still small compared to the antennas that are necessary to keep the link. So, well, I have my solution, and this is what I've been fighting for ages. You cannot do it by antennas. We are too small guys. We are like ants. But you can do it if you exploit the sun as a gravitational lens. So it is as you had an antenna as big as the sun. That works. But that implies a preliminary space mission to the minimal focal distance of the sun as a gravitational lens. So we go back to what I was describing in the beginning. This is what we are studying now. So this is my answer to your first question. Now, my answer, sorry, there was a second question, just a moment. Gaia. Well, I thank you about that, because when I was young, I was working on Gaia. You know, Gaia is a spacecraft from the European Space Agency, not from NASA. I was working at Alenia Spazio in Turin, and I remember going to Cambridge, for instance, 20 years ago to discuss the problem of downloading from Gaia, which is in the Lagrangian point L2 of the Sun-Earth system, because the shield is on the other side. That is, the problem was to download that huge amount of data, we are talking about a billion stars, from that Lagrangian point to Earth. Now, that implies a super compression of data. That is, you have to compress the data on board of the spacecraft before you download them, but you have to compress them in a really nice fashion. Now, in my opinion, that was my part of the story in Gaia. There is only one way to do so. That is, you have to use a principal axis transformation in the Hilbert space spanned by the autocorrelation of the signal plus noise. I know this is difficult mathematics, but essentially the idea is that the Fourier transform is, too stupid. Too stupid, because it uses only sines and cosines. Now, come on, we have been knowing sines and cosines since 200 years ago. Fourier was a friend of Napoleon. So in the 200 years that have elapsed from Napoleon to now, the mathematician like me, I have a PhD in mathematics, have done something better than just using sines and cosines. And so we discovered, the mathematician, we discovered a host of orthonormal bases. For instance, Bessel functions, hypergeometric functions, all these functions of the higher mathematics that the students are terrified to look, because they come from series expansion as solution to the relevant differential equation. But anyway, there is a full, huge zoo of orthonormal systems that are unknown to the ordinary people, but are known to the mathematician. So what I just described for Gaia, that is the compression, takes advantage exactly of that. That is, the transform that I mentioned, that I call the KLT, but goes under different names, like principal axis transformation and so on. This transform does not use sines and cosines only. It uses something much more sophisticated. That is, it discovers the orthonormal frame on the basis of what is the autocorrelation of the signal plus noise. That works. And it has been applied already for other missions. For instance, people don't know, except for the people in the space business, that the Galileo mission to Jupiter, you probably know, you have seen the beautiful picture of Jupiter 20 years ago, was destined to fail, because during the orbit from the Earth to Jupiter, it had to fly by Venus in order to acquire the speed necessary to reach Jupiter in 5 years, okay? But Venus is closer to the sun than the Earth is. So when they got to Venus, they closed the antennas to avoid any problem with the higher temperature. Yeah, but the point is that when they open up the antennas after the Venus flyby, oh my God, 3 ribs were stuck together, so they could not open the antenna anymore. I lived that mission. I was at JPL as a consultant at the time. And we were all shocked, because we regarded the mission as lost. You do not have the antenna. Who cares about the spacecraft going there? If you do not have the antenna, the mission is lost. But then the mathematicians arrive, those guys that are usually despised by the other scientists and engineers and whoever. The mathematicians said, but there is a way. If you reprogram the onboard software, changing the software that was already in existence with this software that I mentioned, the KLT or principal axis transformation, you can save much of the data in the compression process. And this is precisely what was done. In the 5 years that it took for Galileo to reach Jupiter, the whole thing was reprogrammed, and we have the beautiful images. Now, let me tell you something. Of course, NASA doesn't like to say that, because the spirit is always that the mission was a success, period. Of course the mission was a success, even greater than it was imagined. But it was a success because the mathematicians, in this case, were able to solve a problem that had never been faced before. So it is true that it was a success, but you have to be careful, you know, to give Caesar what Caesar deserves. Thank you.
Well, it was a very interesting talk. I have a perhaps naive question. It is because when in the Drake equation, for example, when you put all the fractions you have, I don't see any timing. For example, the duration of the Earth and the appearance of life. It's a tiny fraction, and then I think that I would convolve in the search in other planets because it is not simultaneous.
Yes,
and
you're
so
right.
on, no?
You're absolutely right. Thank you again. This is a very intelligent question. So let me answer. When Drake wrote the equation in 1961, SETI was still unknown even to the scientists. So he did not take all that into account because it would have been necessary to develop a full mathematical theory for that. So he just considered the number of existing civilizations without taking time into consideration. And this is the statistical Drake equation. But let me tell you that there have been many attempts in the following 50 years to generalize the Drake equation to the time Drake equation. It is difficult. It is difficult. But I think that my Evo-SETI theory might lead to that. I just did not have the time to go into the details because you don't have the time, period. But my Evo-SETI theory includes the time. So I leave that to you, to the younger people. You know, it's time for someone else to take over all this stuff. So please, try to find out the time-dependent Drake equation, and you will get a chair. Because of that.
Thank you.
Yes.
Hi.
Okay.
In your here.
Oh, okay. Sure. Thank you.
In your runaway exponential law, if you want to keep the area constant and the peak is increasing, the width should decrease.
And it does.
And what does it mean in a few million years, a civilization that has a lifetime of few hours?
No. Well, okay. No, so far, I took the data from the history book. So there is no civilization that lasted only a few hours. So all the civilization that I consider in my papers lasted at least some centuries. However, you are right in this point, because there is a hidden effect in all this. That is, as long as the time increases, as seen from you this way, the bill of normal becomes narrower and narrower, which means that the corresponding empire, so as to say, lasts for a shorter time. And this is precisely what happened. I didn't show here the Egyptians, the ancient Egyptians, the pharaohs and all that. Now, the Egyptians lasted for 3,000 years. So their bill of normal is extremely long, but also very little in peak, if you do it. Now, today, the empire, say the British Empire, just to make an example, the British Empire lasted a few centuries, to 200, 300 years, no more than that. The peak was very high, but it lasted only a few centuries. Whereas the Romans, just to make one more example, they lasted for about 1,000 years. So the peak is lower, and so the idea of keeping the normalization condition is a good one, because this is the trick that allows you to make the comparison over the times. Otherwise, if you do not accept that, then you mix up and you come up with the Aztecs being more learned than the Spaniards, which is actually not correct. So, okay, thank you. Yes.
Well, I have a comment, or a couple of comments. Yes, you mentioned that about the Aztecs, that they had not used the wheel. That is right, But to move those large stones, they used cylinders, and they had to use pulleys. Otherwise, they couldn't have realized all that engineering feats, and they did that. They did not use the wheel because they did not have any.
The conference will expire
they did not
in 5
have
minutes.
horses or cows or whatever to pull those wheels. And that I want to make a similar comment to us, the present civilization, that we had been carrying our suitcases in our hands until about 20 years ago. I used to carry my suitcases in my hands, and now they have wheels, and I think, my God, that's marvelous. But I mean, what does that mean? That we as human civilization learn about the wheels only 20 years ago?
Yes.
Well, I just wanted.
Thank you so much. This is really important. Thank you so much. I appreciate it.
Thank you for your talk. It's been very impressive. One question: when you talk about four beats between Aztecs and Spaniards, Shannon theory is entropy is measured in logarithms usually. Can you tell us what this difference means exactly? It's a
Okay. Well, I tell you only what I know, okay? Now, let us take this opportunity to explain to the young people in the audience that Claude Shannon, the American engineer and mathematician, published the first book about information theory in the year 1948. Now, Shannon didn't think of anything like that. He was actually trying to find a mathematical way to discover how much information in bits one can convey on a certain telecommunication system. Specifically, he was interested in telegraph, because at that time, telegraph was the most advanced telecommunication system. So in addition to introducing the formula that I showed, that is the Shannon entropy of any probability distribution, which is the number one step, he did find even more. He found another thing, which is called the channel capacity. What is the channel capacity? The channel is the tool for communicating, like the telegraph or the gravitational lens of the sun, which is my channel. Anyway, okay, so the channel is just the tool by which you communicate across distances. But each channel has a specific top amount of information that you can send through the channels. You cannot send whatever you wish up to infinity. No, there is a maximum amount that is given by the so-called channel capacity of Shannon theory, okay? So going back to your question, I used the entropy, that is the first part of the Shannon theory. But in all frankness, I do not know yet how to use the channel capacity. Perhaps some of you young guys may do that. I only tell you one point that I did and published. I was telling you that in order to keep the radio link between stars, we have to use the gravitational lenses of stars. You are astronomers, you know what that means. Or even galaxies, if you want to talk about communication between galaxies, which is not stupid as it looks, because at the center of each galaxy is a black hole. So if you use the black hole as gravitational lens, oh my God, you can transmit data between galaxies. You are an astronomer, you understand. For instance, take M87, this beautiful galaxy with the jet. You know M87. Now, M87 is 60 million light years away from us. So the light takes 60 millions. But if you imagine a system made by the black hole in M87, which is a monster, it has a mass of billions of solar masses, and the black hole at the center of the Milky Way, which is big, but not as big as that, It has a mass of 4 million solar masses. And you imagine to communicate between the two galaxies using these two black holes as gravitational lenses. Then I have published papers, and I can send them to you if you want, proving that you can have a telecommunication link